You can keep it in the just put that somewhat closer to you.
Oh, okay, okay.
You have to switch it on first. There's a button. You just that is off.
There we go. Check the.
If this works, you can test and see.
It's good. Oh, nice. Oh, okay. Yeah. Okay, sounds good. Yeah, I don't. Just hide back here. Okay. Okay. That's good. Oh, okay.
Give it one more minute. All right, great. Let's get started. This is session 6, surveys of the flickering universe and some more galaxy formation. So we're going to get a nice 25-minute talk from Pat Kelly, Here, There, Everywhere, Strongly Lensed Supernovae, JWST, and Roman.
Thanks, Jenny. Great. Well, I'm excited to talk about some new measurements of strongly lensed supernovae and programs that are going on right now to find or to follow up on some new discoveries with James Webb, and then looking forward to Roman. What we might expect and what the prospects are for doing science with strongly lensed supernovae. So I myself became involved in this when we found supernova Refstal in 2014, and I've been working on it ever since. And so I will talk a little bit about why it's interesting. We've finally come up with a measurement or constraints on the Hubble constant from the reappearance of supernova Refstal. We found the Einstein cross here. This is the MAX 1149 galaxy cluster in 2014, and then was predicted to reappear about a year later, and it did. And so we've measured the time delay with about 1.5% precision and used lens models to constrain the Hubble constant in a new independent way. The models for galaxy clusters are different systematics from those that are used to or the models of galaxy scale lenses that are used for time delay cosmography with strongly lensed quasars. So why do we care about the Hubble constant? Well, I'm sure everyone here is familiar with the current tension between the local measurement using type 1a supernovae and calibrated with Cepheids, which gives about 73 kilometers per second per megaparsec. And I updated this to REIS 22 as opposed to 21. I thought people get in trouble with that wrong here. So okay, so then the other measure, so the other most very precise measurement comes from observations of the cosmic microwave background, combined with the assumption of the conventional lambda CDM cosmology, and if you put these two together, you get around 67.4 plus or minus 0.5 kilometers per second per megaparsec. So this is I think more than a 5 sigma tension, and here's a plot showing a number of current constraints on the value of the Hubble constant. And so here are the early values from Planck and then DS and BAO and BBN, and then here's the shoes type 1a local measurement and or late measurement, and then and these are constraints from galaxy scale or quasars that are multiply imaged by galaxy scale lenses, and then we've heard about surface brightness measurements this morning as well. So you can see that if you just consider these most precise measurements, there's a strong tension. And so, of course, if this tension corresponds to a true difference, then this will require a revision of the standard cosmological model. And so it would be great to have independent measurements of the Hubble constant, which have different systematics. And so Refsdal was a Norwegian astronomer, and back in the 1960s, gravitational lensing was sort of in I'd say the dark ages. This was before strongly lensed galaxies had been discovered, or quasars. That wasn't until the 70s that the strongly lensed quasar was found. And so, but he sort of did interesting theoretical exercise and figured out that if you could measure the time delays between the appearance of a supernova in multiple images, you could constrain the Hubble constant. And so he envisioned a supernova. Of course, it's been this very successful effort to measure the value of the Hubble constant using strongly lensed quasars. But actually finding a supernova took another 50 years. So supernovae are simpler in their light curve evolution, and so you don't need to monitor them for as long. Also, if you have a type 1a supernova, you can calibrate its, figure out what its luminosity is from its light curve, and then directly measure the magnification, which breaks some degeneracies. But as I was saying before, also, if we look at supernovae or other objects that are strongly lensed by clusters, the lensing systematics, the modeling systematics, are separate from the existing quasar effort. Okay, so just a little bit of background about gravitational lensing. It's always helpful. And so from general relativity, you get deflection from a point source mass of 4 gm over c squared, the impact parameter b. And so lensing is really just, you can think of it as a coordinate transformation from a source plane to a lens plane, and involves these angular diameter distances. And so if you've got a perfectly well-aligned lensing system, you get an Einstein ring like this. And if you have and so here's one from Sloan. And if you sort of break the symmetry, then you end up with arcs. Here's another example. And there's the nice analogy. The optics of the base of this is from Phil Marshall. The base of a wine glass have optics that are very similar to those of a gravitational lens. And so you can see here, got a nice well-aligned lens, you get an Einstein ring, and then breaks up into multiple arcs, and these are also magnified. So here's what we can see today. So okay, so gravitational lensing. So if you have a piece of glass, a glass lens, you have a geometric delay, and then you also have a delay through the index of refraction as the light passes through the glass. And for gravitational lensing, instead you have a Shapiro delay from the gravitational potential. It both curves space and induces a gravitational time delay. And so you can then compute a time delay surface as the sum of these two. So you've got the Shapiro delay here and a geometric delay, just the path length, if there were no lens there at all. And from Fermat's principle, we know that the images form at the extrema of the time delay surface. And so you can see, so this beta parameter here tells you how well aligned your background source is with your lens. And so if they're perfectly well aligned, you can see you have two extrema here. I mean, in this, you could have an Einstein ring, for example, but in one dimension here, anyway, you can see two extrema. So you would have multiple images of the source. Whereas if you move to less and less alignment, eventually you only have a single extremum. So you would not be in the so-called strong lensing regime, if that makes sense. And so this is an explanation of strong lensing. Strong lensing means you have multiple images. And then you can compute the time delay as in this way from the geometric path length and the lens potential. And so so this is work that that Refstal is responsible for, and so you can write this time delay in terms of the Fermat potential, and if you measured a difference in a relative time delay, so the difference between the arrival of two images, you get delta t over here, and you have delta tau over here for your Fermat potential. So you can compute or infer this ratio of angular diameter distances and the speed of light. And this turns out, inversely proportional to the Hubble constant. And so that's how you get from a time delay measurement of a supernova with a lens model, which gives you the Fermat potential, and to get to inferences about the Hubble constant. Okay, so Refstal made its prediction in 1964. It was successfully applied to strong lens quasars with a huge amount of work from a number of teams. And we were lucky enough to find the first strong lens supernova in 2014. Lens modelers are very excited because this gave them an opportunity to make predictions about the future, about when the supernova would reappear. And so this is a blind test of lens models, and so many of the modelers around the world made predictions. So here we were in October 2015. Some of the models suggested maybe it should have reappeared. I was starting to get a little concerned, and then, however, there was a faint source there, and so the supernova did appear, which was very exciting. The first time we were able to predict the appearance of a supernova on the sky. So we've spent the last however many years it's been doing what we think is a very careful analysis of modeling all the light, the five images of the supernova and their light curves. And it turns out it's an 87A-like supernova, much like supernova 1887A. So we have a compact blue supergiant progenitor, and this gives you this characteristic slowly rising light curve, which you can see here. And so we've used this as well as these detailed simulations where we've modeled the microlensing due to stars in the intracluster medium, as well as the galaxy that's responsible for the Einstein cross, and as well as millilensing due to subhalos and measurement uncertainties as well, and then simulated the light curves and used those to set an error budget for the time delay. You can see here, with multiple image supernova, you can get this fantastic light curve. So here we have, 5 images, and we can shift using our measured time delays, the light curves on top of each other, and so you get this amazing cadence. There's also used a lot of Hubble time to observe it. And what do we come up with? Well, we find 64.6 plus 4.4 minus 4.2. We have a parallel measurement just using 2 of the models that have been previously used for time delay cosmography. But what we've done is weighted the contributions of the models by their ability to reproduce the observables that do not depend on the Hubble constant. So in particular, the magnification ratios, the ratios of the time delays. And And so, you know, if you had a perfect lens model, the 1.5% fractional uncertainty on the time delay would give you a 1.5% measurement of the Hubble constant. So what it turns out is that you know, as you might expect, the lens model dominates the uncertainty. So here's here's our error budget, and so you can see the the cluster halo is the single largest contributor to the uncertainty on the predicted time delay, and therefore the Hubble constant. And so, so this is we're only it's depending on which of these estimates you consider. We're in maybe 1.8 or 1.5% tension with the local supernova measurement, so not significant, but this suggests that this is a new independent measurement, and once we're able to collect a larger sample with Roman and probably other facilities, then we should be able to come up with a new and independent constraint on the Hubble constant to address the tension. So, in fact, very exciting that a strongly lensed cluster lens supernova was discovered in Roger Windhorst's Pearls GTO program, which I also happen to be part of, and Brenda Fry is put in a DD program, and so we're taking follow-up spectroscopy and imaging of 3 images of a type 1a supernova at redshift 1.78, and so this is very exciting. A type 1a supernova, we should be able to measure its magnification from its Lake curve, provide a test of the lens models, and then fortunately the time delays here are expected to be quite long, not a year as it was the case for Refstall, but months, and so that should allow for a fairly precise measurement of the Hubble constant, and so people are hard at work on this object. Okay, and so I thought I would share some of the fairly quick calculations we did for the WFS call, and so what we found was that Roman, if you're able to look in if you look in the high latitude wide area survey, which will have 2 visits, and just confirmed this with Julie the other day to make sure I had that right. But we should expect something like of order 50 strongly lensed supernova to be detected at some phase. Of course, you need the repeat visiting to detect them the second time. So you can only identify them after the second epoch in most cases, and so. But about 10 should be group or cluster scale lens, which would be helpful for having really an independent measurement from the quasar estimates. And then if you just do square root of n scaling, which may or may not work, you need a very well characterized cluster. You would end up with a 2% measurement of H naught. And so I think there's a lot of promise here. Of course, you would have to follow up these discoveries and come up with the time delays. If you have a type 1a supernova, that's actually not too hard because type 1a supernovae Lake curves are very irregular, so you might not need huge numbers of observations. And there's also the higher cadence, deeper field, and that depending on what the area is, you could get something from 2 to 8 strongly lensed supernovae. In that case, you'd have the Lake curves from Roman itself, which would be nice. But if you're, I think in the 5 square degree version, you only get, and according to our calculations, which agree with others in the literature, you'd only get a small number of strongly lensed supernovae. Okay, so I'm going to talk about other interesting things you can do with strongly lensed supernovae, so there are all kinds of fun mysteries we've learned about in more detail today. One of them is that if you look at the Baldwin-Hurlovich-Phillips relation and the emission lines for galaxies near the peak of star formation at redshift 1 and 2, then they seem to occupy a different region in the diagram than say the Sloan galaxies. So what's going on? And we also want to understand, the population of massive stars at, redshifts 1 and 2 and beyond, where, we can't resolve them individually, except for maybe cluster lensed individual stars, but there are so far a huge number of those. And so supernovae provide a way to study the population of massive stars, which are, responsible for the evolution of galaxies, and, provide the ionizing radiation, inject energy into the ISM, and also happen to be the progenitors of the compact remnants that LIGO is detecting. So what might be different? Well, at look-back times of 8 to 12 gig-years, well, you should have, fewer generations of type 1a supernovae, and so, you might have a greater abundance of oxygen and alpha elements from core collapse supernovae. So perhaps, that could explain, say, the BPT diagram. Maybe perhaps the IMF is different, and the star formation conditions are certainly going to be different in some ways. So it turns out that you can actually, through observations of strongly lensed supernovae, characterize in detail stars that explode at high redshift. And so in the nearby universe, there may have been a couple dozen very early published very early observations of supernovae. So if you can catch the explosion of, say, a red supergiant, and in the first, a day or a few days, you can see its black body temperature falling and cooling as the star expands and cools, and this curve depends on the size of the supernova. Its luminosity is not yet powered by radioactivity, so the physics are simpler. You just got the shock that's heated the star, and then it's cooling as it expands. And so, for a handful of events, been able to measure the sizes of stars in the nearby universe that subsequently exploded supernovae. And so, postdoc working with me, Wenlei Chen and I, we found a strongly lensed supernovae at redshift 3. So you can see there are 3 images of it. There's a 4th one here, but it's on top of the galaxy scale lens. And so this was a lot of fun. We made a false color image, and you could see immediately that the color of the supernova changed by eye. So which is really neat. And so this is a single epoch. These images were taken within a couple days of each other in the different bands. But due to the time delay induced by the gravitational lens, you can actually see it change color over a period of days. And so we're able to fit, using a model of the galaxy and the galaxy cluster from Masamune Oguri, we were able to fit the photometry using the lens models to figure out the phase at which we were seeing the supernova, and put a constraint on the size of the star to be about 600 solar radii. So this is, I think it's pretty neat. We're able to measure the size of a star at redshift 3. And so this is with a single epoch of imaging. So, Roman should be able to find objects like this, and do similar kinds of analyses. And so here are more detailed constraints on the envelope, mass, and the radius of the progenitor. And strongly lensed supernovae are magnified, and so if we can find them, we are able to overcome, say, systematics of associated with looking for the core collapse supernova redshift at higher redshift. Sorry, the core collapse supernova rate at higher redshift. And so Wenlei and I, we took Refstal and this supernova I just described, which was in a Hubble Frontier Fields cluster, and used that to put constraints on the rate of core collapse supernovae over the last, or up to redshift 3. And this, it turns out, agrees with the number you would expect given the canonical Milky Way IMF and the Maddow and Dickinson star formation history, whereas previous estimates from Candles and Clash found some discrepancy with the predictions you might expect for those assumptions. It turns out that the dust pair used for the Clash and Candles analysis is not, well, it needs some revision, but it's unclear whether that could explain the difference or not. So I think Roman, by finding magnified supernovae, should be able to contribute to the constraints on the core collapse supernova rate. And then I thought I would just sort of end here by discussing some ongoing observations with, or recent observations with James Webb of strongly lensed supernovae, or lens supernovae, and some of the other applications of them. And so one of them, which was pioneered by Steve Rodney in 2015, was to use a type 1a supernova. As I mentioned, you can figure out what its luminosity is, you can measure its apparent magnitude, and figure out its magnification. And so you can use type 1a supernovae as a unique probe of galaxy cluster models. And galaxy cluster models, of course, important because they're one of our best tools for studying, say, faint galaxies at high redshift, and so they need to be vetted. And so this is a type 1a supernova at about redshift 2 to 3 here, which and so that's this little red dot here that we're using to test lens models. And then here's another type 1a supernova, which was multiply imaged and discovered as part of a Hubble snapshot program. But unfortunately, we caught the trailing image of the supernova, and so we're not able. It's going to be tough to do. Put constraints on the Hubble constant. Justin Pyrrell is working on that, but in any case, what else can we do with these? Well, we can get spectra with James Webb, and detailed analyses of even individual type 1a supernovae are very helpful because for type 1a cosmology, what we want to know is whether the population of type 1a supernovae seen in the nearby universe, low redshifts, or how it is similar or different from that we see at higher redshift, right? So if there's so-called, some evolution in the progenitor populations, which, you might expect, of course, we could examine that with high resolution, high signal noise spectra, with James Webb. Okay, so I think from the high latitude wide area survey, we could, we should detect a large number of lens supernovae, and a significant fraction should be from group and cluster scale lenses. And so hopefully we can put these to work. And if there's a fairly large, high cadence area, we could also get light curves from Roman itself to measure time delays. So strong lensing also is a tool for measuring the supernova rate at high redshift. You get the natural boost from magnification, and due to the time delays in images, we can reconstruct in some cases the early light curves of supernovae, put direct constraints on the size of the stars that are exploding. And then finally, lens type 1a supernovae are really exciting new tools for studying or constraining galaxy cluster models. So.
Awesome, and perfectly in time. Thank you. There was a lot in that talk. So maybe we'll start with the question in the room and then see what we've got online. Yes.
Oh, thank you for the very exciting results and, perspective. This is Minghao Yue from MIT. So I apologize if I missed it. So you mentioned there are lens supernovae, type 1a supernovae. So, type 1a supernovae itself can be a standard candle, right? It can measure H0. And with a lens supernovae, you can measure H0 in another way. So have you tried to compare the results from the supernovae light curve itself and the lens model about the Hubble constant? Again, I apologize if I missed it, but I'm very interested in such kind of comparison.
Well, I guess we're supposed to leave.